So Hugh Thomas is definitely a friend of the conference in that he's been on the organizing committee for CAAC 6 times. So that makes him the winner of the most frequent organizer of CAAC, except for Sarah Faridi Award. Today he's going to speak on, well, titles change a bit. It looked like a system of equations associated to a surface.
Right. Well, so thank you very much for the opportunity to speak here today. It's always a pleasure to be speaking at CAAC. For one thing, it means I must not be organizing this year. That's also a pleasure. So this topic is a little bit, maybe a little bit, off the beaten track for CAAC, and I also, I guess, changed how I wanted to focus the talk subsequent to my submission of the abstract. So I apologize if you were really particularly eager to hear about exactly the talk as described in the abstract, because somehow trying to figure out how to give a 20-minute talk on this, I keep changing my mind about what I want to try to do in 20 minutes. So anyway, this project is joint work with actually, well, so Pierre-Guy Plamondon, who is a representation theorist, and a bunch of physicists. And so I'm not going to be really talking about the physics, but I'm hoping to say enough about it that it's sort of motivational and, it piques your interest. I'm definitely not a physicist myself, but I can try to answer questions about the physics at the end if you like. Very possibly I won't be able to do a great job, but it has it's been fun working on this project with actual physicists, and I encourage people to talk to physicists if you get the chance. So let's get started. So let's start with an oriented surface with boundary and a set of marked points on a boundary, and at least one marked point on each boundary component. So the surface could look like a disk with some marked points on the boundary. It could look like this, which is an annulus, so that the actual surface part is what's between the two circles. So there's just a couple of examples. And then we're going to be interested in the set of curves running from boundary to boundary and avoiding the marked points, and up to homotopies, which preserve those properties, and excluding some silly curves that are just contractible, or curves that are just cutting off a single marked point. So the curves that we want on this disk look like this or this. Those are the two curves. Those are the two classes of curves that we're interested in. If I would have drawn a curve that was like this, that's not really a different curve. That's just the same curve again. Examples of curves that we don't want are something like that or something like that. So those are somehow too small and they're just excluded. The combinatorics of the disk is actually, of these curves on the disk is actually pretty familiar, to people who do cluster algebras, for example. Once we get to other surfaces, life gets quite a bit more complicated, because you start to have, you can see this is a perfectly good curve, but it would also be a perfectly good curve, and it would be a different curve if I would have wound around a different number of times, because there's no homotopy that would take me from, from the first curve to the second curve. Those are different curves, and you could wind any number of times, and those would all be different curves. So if we're not in the disk case, we actually have to deal with an infinite number of curves. And now what I'm going to do is I'm going to introduce a variable for each curve, a variable u gamma for each curve, gamma. And I'm going to consider a system of equations, one equation for each curve. And so the equation says u gamma plus the product over all the curves of u delta to the number of intersections between delta and gamma. So the sum of these two things should be 1. So we have a system of infinitely many equations in infinitely many unknowns. Here, the intersection that actually means the minimal number of intersection points. So you have to draw the curves in a minimal way, so that to make that well defined. Okay. And right, and so let me just look again at the example that so there's two, as I said, there's two curves that you can, the set of curves for the four puncture or the disk with 4 marked points. There's just two of them. And the equation is just U gamma plus U delta equals 1. So that, if you like, is the equation corresponding to gamma. But if you were to write down the equation corresponding to delta, you'd see that it is just U delta plus U gamma equals 1. So we've written down the same equation twice. Anyway, and we can solve that equation. Now, there's a couple of things that might be, a couple of questions that might be in your mind at this point. One of those questions is, why would you possibly write down a system of infinitely many equations, infinitely many unknowns, and hope to get anywhere with it? And why would you want to solve it in the first place anyway? So that's one question. And the second question is, why would you talk about this at CAAC? And I will try to address both of those questions. So to begin with, what is the motivation? Why would we want to do this? Well, in the case that the surface and the set of marked points is just a disk with marked points on the boundary, then this system was solved in 1969 by Koba and Nielsen. And they used it to write down what's called the string tree amplitude. So this is, okay, yeah, so let me just sort of try to say a little bit about what's going on in this, oops, a little bit about what's going on in this formula. So the P's, so we're just somehow physicsy way, which I don't really pretend to understand, is describing what happens when particles scatter. So you have a bunch of incoming particles with some momenta, and they're going to interact and they're going to zoom off, and you want to describe what happens, and you wind up wanting to do that by describing this amplitude function. Okay, so what does the amplitude function look like? Well, it's an integral over the region where the U gets positive. So if we think of solving the equations, so we simultaneously know what all the U gammas, I mean, so we can think of the algebraic variety cut out by the equations, and we look at the piece of that algebraic variety where all the U gammas are positive. And then we take a product of the U gammas raised to the P's, which are the momenta, well, or which are, I mean, a re-encoding of momentum. Anyway, so that's the string tree amplitude. And so that is the tree amplitude, because it's the 0th order approximation, which is associated to a surface, namely the disk, with genus 0. And so the idea is that in string theory, you should expect corrections to this answer associated to the disk, and the correction should be associated to surfaces of higher genus. And so that's where, so already in 1969, it was understood that you should try to write this down. You should try to do this same thing that Koba and Nielsen had done, but instead of working with the disk, which was the only case they had thought about, you should try to work with surfaces of higher genus and try to do somehow the same thing. And that didn't really, people didn't get that to work out at all. They got totally stuck. And for some good reasons. I mean, as I already mentioned, there's now infinitely many curves. Anyway, there's a whole bunch of things that kind of go wrong, and they didn't have a lot of, well, and so 50 years have gone by, and we have some more math around to help us now. And as part of NEMA's approach to scattering amplitudes, this problem kind of reappeared as an important problem to be thinking about. And so that's why, so that's what's going on. Why would I be talking about it at CAAC? Well, the reason is that algebra and combinatorics are going to be relevant to solving it. And specifically, I want to describe a solution using a formal power series. So I'm trying to solve the system of equations that we had over here by defining a formal power series for each of the U gammas or gammas in this set of curves. So that's the goal. So in order to get something that we feel more like we could handle as combinatorialists, we're going to want to take this set of curves, which we feel like, oh, that's some geometrical thing that, you know, curves, yuck, right? We want some combinatorics. So how do we get some combinatorics? Well, we want to combinatorialize our curves. What we're going to do is we're going to take our surface and we're going to triangulate it. So now, so I have my surface here, which is now this annulus is my surface, and I've drawn a triangulation in green. And now here is one example of a curve that I could draw. And my point is that I can think about that curve really as a sequence of edges that I cross. So I started on this edge, and then I crossed this edge, and then I crossed this edge, and then I crossed this edge, and then I ended on this edge. So we could actually think of that as a walk in a graph. So the graph is what's drawn over here in red and orange. I started here, and then I crossed this edge, and then I crossed this edge, and then I crossed this edge, and then I crossed that edge, so that this curve really turns into a walk in the graph. So the graph just amounts to saying each time I see a triangle in my triangulation, well, I can go from one edge to the next edge, or from this edge to this edge, or from this edge to this edge. And for some technical reason, which we'll see why in a moment, I've oriented the edges. But that doesn't have anything to do with the walks. That's gonna turn out to be important on the next slide. So this walk defines a representation of the quiver Q hat. So this graph, I'm now going to start calling it a quiver because I'm going to do representation theory. So and just to sort of make it clear, the representation is I'm just going to put a copy of my ground field complex numbers at each of the vertices, and I'm going to put linear maps between them that are just multiplied by 1. So this is a very simple representation. The idea is that for all the other vertices, I'm just going to put 0. Okay, so this defines a representation of this quiver. As in Benjamin's talk, if you were there for Benjamin's talk. And notice that it actually still defines a representation, even if the walk were more complicated. If the walk were to go around and then wind up, wind up visiting some vertices twice, you would write down, if you did this sort of a thing, you would write down this longer walk. And you wind up putting a vector space at some of the vertices that is more than one dimensional, but this same prescription really gives you a representation. But not just any representation, because the walk is always going to go from here to here and then leave, or from here to here and then leave. It's never going to do, a sort of dance around inside the triangle right away. So what that is telling us is that the composition of any two of these arrows is 0. At any one piece of the walk, and then the way we build up the whole representation, that is actually going to be true for the representation. So we're actually getting a representation of this quiver with the relations that inside any triangle we have composition of 2 consecutive arrows is 0. So that quiver with relations is gentle. If you remember a definition from Benjamin's talk, if you don't, that's fine. It doesn't really matter. But the great thing about gentle algebra is that unlike general finite dimensional algebras, the indecomposable representations are classified. They come in two kinds, strings and bands. And for today, I'm sort of giving it, I've sort of simplified my life and I'm ignoring the bands. We don't really want to do that. We really want to include the bands, but it turns out that the bands don't screw anything up for the strings. So if I just, I still have a meaningful story if I just talk about the strings. So that's what I'm doing today. In fact, what we'd really want for the string theory would include both kinds of representations. But so what we're going to do now is so another thing about the representations that I was getting is that they started and ended on the boundary, but otherwise they weren't going to visit the boundary vertices. So if I would like to get a bijection between some representation theory and some curves, so I'm going to want to throw away the boundary vertices as well. And so it turns out that there's a bijection between the string representations and the curves. Okay, so there's this finite number of like one for each internal arc. Funny thing is that are not exactly representations. Don't worry about that unless you are like an expert already in like tau tilting theory or this kind of story. Basically, don't worry about these guys. The idea is curves really correspond to representations in the way that I described. And this is going to be my notation for how that works. So there's a thing you can do to a curve. So you can just rotate one endpoint or the other endpoint or both endpoints. And it's a really cool fact that the Auslander-Wrighton translation, if you've run across Auslander-Wrighton translation before, it's an important thing you can do to a module. And it is just obtained by rotating both endpoints, like one step along the boundary. And the really nifty thing is, from the point of view of, for my purposes today, the nifty thing is that this counting intersections of curves can be translated into the representation theory as well. So we not only have a translation of the objects, but we also have a translation of the key thing that we needed to do with curves, which is count intersections. And it turns out that the number of intersections is the sum of the dimensions of two Hom spaces. And so we can rewrite the equations that we had at the beginning in terms of curves in terms of representations. And this is kind of interesting because it gives us the we now have a problem that doesn't have any curves in it anymore. And so you could just have written down these equations to begin with and just said, what's going on with these equations? You could do that for any finite dimensional algebra. It seems like this is not quite the right thing to do in a general finite dimensional algebra, but for a finite dimensional algebra with only finite many representations up to isomorphism, this is the right thing to do. And these equations are pretty interesting. And that was sort of the way into this talk that I had originally, I guess, imagined that I was going to start from. But I thought it'd be more fun to talk about the physics. I don't know. So we have a problem, and I'm nearly out of time. But fortunately, I don't want to say very much more, except to tell you how to solve the problem once we have formulated the problem in terms of representation theory. So when we have a module like this, there's a thing called the F polynomial of the module, which is a generating function for the order ideals of a post set. So here's my module, and this is not the usual definition of F polynomial, but it's equivalent. So here's my module. I just drew it over here. I can think of this module, it's a sequence of vertices with arrows between them. I can interpret that as the Hasse diagram of a poset. It's a sort of funny poset. I mean, it's kind of very one-dimensional, but anyway, I can do that. And then I can write down a power series, a formal power series, in a set of variables corresponding to the edges of the triangulation for the set of all the order ideals in the poset. And then we can solve the problem. So the solution is that U gamma is given by this ratio of these formal power series associated with the representations, which are coming from gamma. And this, I'm lying slightly in the case that M gamma is shifted projective. Anyway, that's what I wanted to tell you, really. Once we have this, since I'm out of time, I will just stop in a moment. But now that we have this, we can then start to struggle with the question of, can we write down an integral like the string amplitude of Coben-Nielsen, and can we study that? We can also ask ourselves other questions. We can in particular, one question that I'm curious about but haven't really thought about yet is this solution depends on the choice of triangulation, and as you change triangulations, you're effectively mutating. Well, that's some kind of mutation of the solutions. You're like changing your starting cluster, if you like, and we haven't really looked into how that works. In type A, this is really related to cluster algebras from surfaces, but it isn't quite cluster algebras from surfaces, or sorry, it's X cluster algebras, not A cluster algebras. Anyway, it's not quite that. It doesn't seem to be quite that once you leave the disk setting. Anyway, I should stop here. So thank you very much for your attention.
Thank you. Is there anybody who has questions? Kaveh asks, what should one expect when you take bands into consideration?
That's a great question. Thank you, Kaveh. So you should, you want to have the same, okay, so I really want to write down an equation for bands as well. And okay, so I really want to write down the same equation for bands. The funny thing is that the bands don't really show up in this term. And the reason for that seems to be that bands are indexed by bands. To a band module, you also have a non-zero complex number that enters in the definition. And so there's a moduli which is associated to this choice of a non-zero complex number. And the Euler characteristic of the non-zero complex numbers is 0. And that seems to be, well, that's at least, the explanation that I like for why you would expect there to be a term here for the bands, but it's somehow weighted by that 0 Euler characteristic, which makes it disappear. So that's why even once we have the bands, that doesn't actually change this equation. For the bands themselves, you want to write down an equation that is very much this equation, though there you do get a little bit of a contribution from other bands that are associated with the same curve in the second term. I don't know, hopefully that maybe says a little something.
Are there any other questions? If not, let's thank the speaker again.
Thank you.
And we have a coffee break now, which I think we can stay on schedule. It's 15 minutes, but we'll cut it short to 10 and restart at 11:10.